This is part 4 of atomic theory, electron dot structures, also called Lewis dot structures, but that's mostly what it's referred to when you're looking at bonding, which we'll get into a little bit later on. So in part 1 of this explained atomic theory. Part 2 we explained electron configuration. Part 3 noble gas configuration. And finally part 4, how do we build these electron dot structures, which will ultimately help us figure out how do these different types of elements bond together. And it'll help us understand how to form ionic bonds and covalent bonds. So in electron dot structures, here's basically the general rules. We're only going to show the valence electrons, which are the electrons that live around the outside edge. We don't care about anything that's in closer to the nucleus because the outside edge electrons are the ones that determine bonding. The element symbol in the middle refers to the element, but it's also going to include all the unseen electrons. The dots that we're going to put on these are only valence electrons, and we put them around the symbol one by one in a rotating order until they have to pair up. The max we'll have is 8 electrons, so that's 2 pairs, 2, 2, 2, 2. So, just to give you a few examples, this is oxygen. Now, oxygen has 8 electrons, but when we're looking at the electron dot structure, we only see 8 of them here. The reason for that is the innermost energy level, the 1n, can hold 2 electrons. Any electrons that come in after that will no longer fit inside of there. So they will work their way out to the next energy level. If this was all the way filled up for oxygen, which means maybe it went and gained a couple of electrons somehow, it would look this way. Now, what happens with with oxygen when it's like this, it would like to have 8 in its outermost shell. So it does things like goes out and finds a couple hydrogens that are willing to share their electrons, and then we've just created H2O, or water. So, how do we draw these out? Now, if you don't know how to draw the electron configurations, you'll need to go back and view those other parts to this. But once you've figured that out and you know how to operate your periodic table, you can look at phosphorus, for example, which has 15 electrons, or chlorine, which has 17 electrons. So let's look at phosphorus. Phosphorus is number 15 on the periodic table, and this will sort of recap what we did in part 2, and we'll figure out what is the electron configuration for phosphorus. To do that, we work our way just like we have done before. The 1s holds 2 electrons, so we've used up 2 electrons. Sorry, we need to get up to 15 electrons. The 2s holds 2 electrons, so now we're up to a total of 4 electrons. The 2p holds 6, and the 3s holds 2, so that's a total of 8. 8 plus 4, that equals 12. So we're up to 12. We need to account for 3 more. Those 3 more are going to end up right here in the 3p. Now the 3p could hold 6, but we don't have 6 to put in there, so we only have 3. Now if we come over and we start to write this out, we end up with 1s2, so I'm just working my way back through these, just like I drew the lines. I've got 1s2, 2s2, 2p6, 3s2, and 3p3. Now, if I find phosphorus on the periodic table and then I work my way backwards until I hit the next closest noble gas, I'll find that I run into neon, and neon is 10. So neon has 10, and it's a noble gas, so it's stable. If I count these up, I've got 2, 4, and 6 more is 10. That must be the configuration for neon. So I could take that out and write Ne down here, and then write my leftovers, which are the 3s2, 3p3. And the remaining electrons I have here are how many valence electrons I have. In this case, I have 5. So I'm going to clear the screen. We need to remember we have 5 valence electrons. To write that out, I put my elemental symbol, and then I put my valence electrons. 1, 2, 3, 4, 5. This is the electron configuration or the electron dot structure for phosphorus. Let's look at one more, chlorine, number 17 on the periodic table. And to recap how we do all of this, you can fast forward through it if you remember these. We need to work our way up to 17 electrons. The 1s holds 2, so we're up to 2 electrons. The 2s holds 2, we're at a total of 4 electrons. The 2p holds 6. The 3s holds 2, so that's 8 more together. 8 plus 4 is 12. We're at 12 electrons, and we want to get to 17 electrons. So we've got 5 more we need to account for. Now this 3p right here would hold 6, but we only have 5 more. So when we put those in there, we've gotten our total up to 17 electrons, and we can write this out. So we'll come back through each one of these and write them out as we see them. We've got 1s2 right here. We've got 2s2 right here. We've got 2p6. Work our way up to 3s2 and finally 3p5. When we find chlorine on the periodic table, we need to work our way backwards until we run into the nearest noble gas. When we do that, we're going to find out that the nearest noble gas for this one is neon. And neon has 10 electrons. So if we count these up, we've got 2, 4, and 6 more. That equals 10. So this must be the electron configuration for neon, which means we can pull that out and write Ne, and then write the leftovers. And I somehow included too much in there. Let me fix that. There we go. We've got the 3s2 and the 3p5. Now, that means we have 2 and 5 more. We have 7 electrons left over. So in chlorine, we must have 7 valence electrons. Let me wipe the screen, and we'll see how we write chlorine for the electron configuration, or for the electron dot structure. The elemental symbol for chlorine is Cl, and we've got 1, 2, 3, 4, 5, 6, 7. This is the structure for chlorine. So hopefully that takes you all the way through and gives you a better understanding. One of the trickier parts of this is the D block. The D block is in here, and we will talk about this in a later unit and understand how the D block plays a little bit differently than these other areas. But we'll get to that next time. So good luck.